Hi, in this video, I explain and solve all the free response questions to the AP Stats exam of this year, 2023. I previously made 6 separate videos of the solutions to the 6 questions. So if you prefer to watch them that way, check the description section below for the links. Question 1. As part of a study on the chemistry of Alaskan streams, researchers took water samples from many streams with temperatures colder than 8 degrees C and from many streams with temperatures warmer than 8 degrees C. So already you see 2 populations and samples taken independently from the 2. For each sample, the researchers measured the dissolved oxygen concentration in milligrams per liter. We're looking at a quantitative or numerical variable. Part A. The researchers constructed the histogram shown for the dissolved oxygen concentration in streams from the sample with temperatures colder than 8 degrees C. So this is the colder side. Based on the histogram, describe the distribution of dissolved oxygen concentration in streams with water temperatures colder than 8 degrees C. So it's this histogram that they want us to describe. So it's a question about describing a distribution of a quantitative variable. The common approach is to describe the shape, which consists of how many modes, unimodal, bimodal, and the skewness. Is it skewed to the left or skewed to the right? Center, spread, and special points such as outliers. This is the shape. Outliers, center, spread. So many people teach it as SOCS, SOCS, for ease of remembering. I like to put outliers at the end. Describe the distribution. The distribution of, and then we need context. Context is a big deal in AP statistics. So all of this context, put it all in your answer if you can, or if you're tired of doing that, do some sort of abbreviation. I'll just put the whole thing in. The shape, modes, and skewness is unimodal, one mode here, and is skewed to the left. The mode is here, and the rounded number for that is 11. But really, because it's a decimal, so it's really between 11 and 12. All right, now for the rest of the center and the spread and outliers and all that, I can actually compute the mean and standard deviation by converting this histogram into a table. So for example, this bar right here, I would put it in a table of X and frequency of X as an X value of, well, it's anywhere between 2 and 3, right? It could be 2 point something. So the advice that most people give you is to enter it as a 2.5 with a frequency of 1. Over here is a 3.5 with a frequency of 0. You can put it in or you can ignore it. 4.5 with a frequency of 1. 5.5 with a frequency of 1. 6.5 with a frequency of 13, etc., all the way to the end with a 13.5 and a frequency of 46. So you have all the stuff in between here. If instead of 2.5, 4.5, you enter as 2, 4, you probably will come up with an answer that's close enough. Your mean will probably be 0.5 below my mean. Your standard deviation will probably be the same, probably be close enough that it's acceptable, because even the 2.5 is just a guess, right? We don't know where it is between 2 and 3, so we guess it is probably nearer to 2.5 than any other number in that range, but it could be at 2.0 exactly for all we know. This approach is a commonly used approach, but it's not the only approach, and it certainly cannot claim to be better than everyone else. So I would put all of that into my calculator If I were using a TI, it will be 1 var stats with L1 comma L2. That's for the TI. If I were using the Casio, I'll be setting the X list and the frequency list. And then after that, I'll do calc 1 var. Either way, I would end up with the same answers. And I'd write it down here, approximate mean, 11.1. Standard deviation S is equal to 1.726. That will take care of the center and the spread. I might as well put down the median. And now about outliers. Because I ran the summary statistics, I know what the Q1 and IQR are. So with Q1 equals 10.5, IQR equals 2, thus outliers below 7.5. And there are 13, 14, 15, 16 of them. Part B, the researchers computed the summary statistics shown in the table above for the dissolved oxygen concentration in streams from the sample with water temperature warmer than 8 degrees C. Use the summary statistic to construct a box plot. Do not indicate outliers, so you don't have to do that 1.5 times IQR. The whiskers would go all the way out to the minimum and the maximum. For box plots, I need these numbers. I don't really need these two numbers. I may use them for something else later, but right now I just need those numbers. So 2.1 is around here. Q1 is 4.39, which is around here. Median is 5.43 around here. Q3 6.12. And maximum is at 13.45. Draw my box around the middle part and draw my whiskers out to the min and to the max. Now part C. The researchers believe that streams with higher dissolved oxygen concentration are generally healthier for wildlife. Which streams are generally healthier for wildlife? Those with water colder than or warmer than, using characteristics of the distribution of dissolved oxygen. Justify your answer. Basically, they're saying more oxygen is better. So which one has more oxygen? Regardless of how much calculation you did or did not do in part A, you can still answer this question. Part B basically says that 75% of the sample have oxygen of 6.12 or below. Whereas part A, if you look at the distribution itself, 6.12 and above captures the vast majority of the samples. So even though you may have missed most of the calculations or you didn't think of doing the calculations, you can still answer part C. I will pretend I didn't do any calculation in part A and answer as far as I can see in the graphs. For water colder than 8 degrees C, vast proportion of the samples, and I can just add them up and I see that it's 429, whereas below 7 is just 16. So 429 minus 16 is 413. Have more than 7 mg per liter oxygen. While 75% of samples warmer than 8 degrees C have. And now I'm doing a comparison question. So I need comparison word. Have 6 mg per liter concentration. Here's my comparison word, lower than 7. So that's what I get if all I have are the two graphs, the box plot, which I assume a lot of people can do, and the histogram that's already given. I'm doing all this without any calculation. If I go into the calculation, then I can start comparing other things. Holder mean concentration is 11.1. Higher comparison word. Warmer mean of 5.54. Holder median of 11.5 is higher than warmer median of 5.43. I am not actually gonna run a 2-sample t-test for the means because I don't know the sample size of this sample. I don't know how many of the warmer samples they took. There's nothing in the description. So first of all, I cannot plug in the number for my calculator. And second of all, I cannot check the conditions are met. I don't know if it's more than 30. It's definitely not symmetric. It's very skewed. So I would prefer to have a large sample, and I don't know if I have a large sample. So part C is basically a descriptive question. Actually, I'm going to change the 413 divided by 429 into a percent. Just fix a few wordings here and there. And since I'm giving the standard deviations, I might as well use it. And it's a good idea. If you think in terms of ANOVA, right? You want to show that the two are not overlapping by a lot. Both have small SDs. Decoder, S is equal to 1.1. Warmer S is equal to 1.7. While the difference in mean is this mean is actually 11.1 actually. So difference in means is 5.56. I want a comparison word more than 3 times either standard deviations. So very little overlap. So this, I've used all the information that I can. I feel good about my answer. Now I have to answer the actual question asked. The question asks, which streams are generally healthier for wildlife? I have to answer that. Because colder streams, I'm adding more words now because I really want to put in a lot of comparison words. More oxygen generally. I'm using the word generally because it's in the question. Colder streams are generally better for wildlife. Question 2. A developer wants to know whether adding fibers to concrete used in paving driveways will reduce the severity of cracking because any driveway with severe cracks will have to be repaired by the developer. The developer conducts a completely randomized experiment with 60 new homes that need driveways. 30 of the driveways will be randomly assigned to receive concrete that contains fibers, and the other 30 driveways will receive concrete that does not contain fibers. After 1 year, the developer will record the severity of cracks in each driveway on a scale of 0 to 10, with 0 representing not cracked at all and 10 representing severely cracked. Okay, so a score, a numerical score, a quantitative variable. Part A, based on the information provided about the developer's experiment, identify each of the following. Experimental units. There are 60 units and each is receiving something, each is receiving concrete. So those are the experiment units, or the 60 driveway. This is very similar to question 2 last year, 2022, and all they really needed was the experiment units down to the single unit. So you don't need to say more. If you want to say more, you can say things like that received the concrete, but I don't think it's that necessary. The treatments, and don't forget that the placebo always counts as a treatment. In this case, it's kind of easy to see that, you know, once you identify the driveways as the 60 driveways, then yeah, whatever they are getting is a treatment. So the treatments are the concrete with fibers, and the concrete without fibers. And the response variable is the output from the experiment, and the output is that they record the severity of cracks, the score from 0 to 10 of severity of cracks. Part B, describe an appropriate method the developer could use to randomly assign concrete that contains fibers and concrete that does not contain fibers to the 60 driveways. For a random assignment question like this, you want to make sure of two things. One is the probability. It should be even. In this case, there are two choices, either with fiber or without fiber. Then each choice should have a 50-50 chance. And the second thing you need to worry about or ensure is the numerical number of each outcome. Since we have 60 driveways divided into 2, it's got to be 30-30 and not something like 31-29. Here's an answer that would be wrong. You flip a coin. Great. So that's 50-50. Heads with fiber, tails without fiber, 50-50, but it may not guarantee 30 each, because there is an extremely high likelihood that if you flip a coin 60 times, then there will be more of one than the other, either more heads than tails or more tails than heads. So that would be a wrong answer. I'm going to show two possible right answers. One is like flip a coin, where the randomization is done on each individual. And the second approach, which is my personal preference, but probably I'm in the minority, is to randomize the whole list and then just chop it in half. Flip a coin. Repeat, but instead of just repeat all the way, you repeat until there's 30 of something. Then the rest get the other. You may feel kind of uneasy about this because it feels like you're flipping a coin, you get either fiber or no fiber. And then once you get 30 of something, then the rest of them, they all get the same thing. It feels wrong, but it turns out that is perfectly fine. It feels wrong because you have a string of people at the end that all get the same treatment. They all get either all fiber or they all get either all no fiber. But it turns out to be perfectly fine. Nonetheless, because it feels kind of weird to me, it's not my first preference. You could have a whole bunch of fibers at the end, but you could also have a whole bunch of not fibers at the end. So at the end, each of position is still 50-50. Right, so that's one way of doing it, where you do it randomly on each person at a time. Another way of doing it is to randomize the entire list. For example, by putting them in a hat, shake well, and blindly pull them out in order. Then what you have is a big list that's already all random. Then you might as well just do 30-30 like this. Or if you want it to feel more random, you can alternate them. Whatever, it really doesn't matter. The whole list is already in random order. So those are two possible answers to part B. Part C. Suppose the developer finds that there is a statistically significant reduction in the mean severity of cracks in driveways using the concrete that contains fibers compared to the driveways using concrete that does not contain fibers. In terms of the developer's conclusion, what is the benefit of randomly assigning the driveways to either the concrete that contains fibers or the concrete that does not contain fibers? This is very similar to question 2B in 2022. That question is a little bit ambiguous. So the wording here makes it clearer. They want you to identify a benefit of something, and they want to specifically want you to do it in terms of the developer's conclusion. Why do we randomly assign things? The general idea usually is so that if there's some sort of external factor, like a confounding factor or the lurking variable, then it sort of evens out when you randomly assign things. For example, you may think that what kind of vehicle the homeowner is using may affect the driveway, right? If you have a huge big car that sits on the driveway a lot, then that's one thing. Whereas if you have a small car and it only drives across the driveway into the garage, then that's a different thing. Well, if you randomly assign them into two groups, then you're kind of hoping that if there's a house with big cars that sit on the driveway in the fiber group, but because you were doing things randomly, then there's a chance there will be another one in the non-fiber group. Basically, you want to even things out by randomly assigning things. And how does that affect the final conclusion? This is a hypothesis testing answer that there is a statistically significant difference. You can think of it like it's a two independent mean t-test. So how does the fact that you can even out the effects of the vehicles affect the final answer? Well, it makes the final answer more correct. When you're saying that it really is the difference between the concrete, then you're able to ignore or overcome the effects of the other variables. So let's write it like that. Is to distinguish between the effect of fiber. By the way, when you write these things, be careful of words implying. You know what? I want a comparison word is, so I say to better distinguish between the effective fiber versus the confounding effect of other factors such as vehicle type. Now, what we have here is a controlled experiment, and controlled experiments are supposed to allow us to prove causation. So we might as well say something more about causation, just in case. I'm going to say it reduces the risk of a wrong conclusion on what led to the reduction in severity of cracks. Right, putting the word fiber, putting the word vehicle type and cracks gets me context. Right? Also, context is always an important thing to put in an AP Stats answer. Question 3. Bath fizzies are mineral tablets that dissolve and create bubbles when added to bath water. In order to increase sales, the Fizzy Bath Company has produced a new line of bath fizzies that have a cash price in every bath fizzy. Let the random variable X represent the dollar value of the cash price in a bath fizzy. The probability distribution of X is shown in the table. Right, there's a table. Here are all the different values of X, and here are all the different probability values, except that there's a number here that's not filled in. And sure enough, based on the probability distribution of X, answer the following. Subpart I, calculate the proportion of bath fizzies that contain $1. So sure enough, they want the probability over there. Okay, probability of X equals $1 is 1 minus the sum of the probability that X is not equal to $1, and that is equal to 1 minus all the rest of the probabilities. 0.2 plus 0.05 plus another 0.05 plus 0.01 plus another 0.01, and that is equal to 1 minus 0.32, which is 0.68. But I calculate the proportion of bath fizzies that contain at least $10. At least $10 means all of these people. And that means 10, 20, 50, 100. And it is equal to 0.12. But B, based on the probability distribution of X, calculate the probability that a randomly selected bath fizzy contains $100, given that it contains at least $10. Well, the probability of containing $100 is 0.01, so 0.01 contains $100. Out of 0.12, at least 10. Therefore, the probability of having $100, given that we're getting at least 10, is 0.01 divided by 0.12, which is the same as 1 divided by 12, which is 0.0833 repeating. So we're rounded to 0.083. Now, if you want to use the conditional probability formula, you can. Probability of B given A is probability of A and B divided by probability of A. So this part here goes in the denominator, and both of them go in the numerator. Well, to be 100 and to be at least 10 is just 100, because once you are 100, you are at least 10. So this is actually the same as probability of 100 divided by probability of at least 10. And therefore, we have 0.01 divided by 0.12. That would be the second solution using the formula. I think if you're using this formula, the risk is that you're calculating that as multiplying the two of them together, and you're going to end up getting the wrong answer. Part C, based on the probability distribution of X, calculate and interpret the expected value distribution of the cash prize in the bath fizzies. The expected value of X is equal to the sum of X times probability of X. Just plug in all the numbers. So all the numbers are here with the 0.68 here going into the box of $1. One times 0.68, that's $1, plus 5 times 0.2, 10 times 0.05, 20 times 0.05, 50 times 0.01, 100 times 0.01 is 4.68. And what does this mean? This means, interpret. It's an expected value, so it's something you expect. And these things involving probability are always things in the long run, according to the law of large numbers. So we can say that in the long run, over many bath fizzies, the amount in each fizzy is expected to average 4.68. That's the interpretation of an expected value. Now, part D, the fizzy bath company would like to sell the bath fizzies in France, where the currency is euros. Suppose the conversion rate for dollars to euros is $1 equals 0.89 euros. Using your expected value for part C, calculate the expected value in euros of the distribution of the cash prize in the bath fizzies. Show your work. If I let Y be the value in euros, then Y is 0.89 times X. So the expected value of Y is equal to the expected value of 0.89X. And then a property of expected value is that you can factor these coefficients out. And so I can multiply it like that, and I get 4.1652 euros. This is a full answer. It includes this part that justifies how you can just take the 4.68 and you multiply by 0.89. Now, I don't know what the rubric will do to you if all you have is this. I don't know. Are you allowed to just assume that $1 can just convert to euros directly? Or do you have to have this part that mathematically justifies? I don't know. Question 4. A medical researcher completed a study comparing an omega-3 fatty acid supplement to a placebo in the treatment of irritability in patients with a certain medical condition. 19 patients with a medical condition volunteered to participate in the study. The study was conducted using the following weekly schedule. Week 1, each patient took a randomly assigned treatment, omega-3 supplement, or placebo. Week 2, the patients did not take either the omega-3 supplement or the placebo. This was necessary to reduce the possibility of any carryover effects from the assigned treatment taken during week 1. Week 3, each patient took the treatment, omega-3 supplement or placebo, that they did not take during week 1. When you read a question, you need to make sure you understand what's going on, what the setup is, what kind of experiment they're conducting. If you read up to here and you get it, great. But if you did not get it, you need to slow down and maybe draw some diagram or something. For example, let's say that I don't get it. Then I look at week 1. Each patient took a randomly assigned treatment. Is either this omega-3 treatment or placebo. And then in week 3, they took the treatment that they did not take during week 1. That means the omega-3 people now take the placebo, and the placebo people now take the omega-3 supplement. And the part in between is so that the system have the time to wash the effect out. At the end of week 1 and week 3, each patient's irritability was given a score on a scale from 0 to 10, with 0 representing no irritability and 10 representing the highest level of irritability. So at the beginning, they get a score. At the end, they also get a score. And the score is 0 is good and 10 is bad. For each patient, the two irritability scores and the difference in their scores, placebo minus omega-3. So it's always placebo minus omega-3. For the blue people, it's subtracted this way, and for the red people, it's subtracted that way. Always placebo minus omega-3. What does this difference mean? If everything works perfectly, then the placebo have no effect, and the omega-3 totally cure the person of irritability. That means with the placebo, the score will be whatever it is, let's call it X, some positive X. But with omega-3, assuming it works perfectly, it should go all the way down to 0. So you go X minus 0, you end up with equal to X, which is a positive number. For example, you could start out with maximum irritability, and omega-3 cures you. 10 minus 0 is equal to 10, which is a positive number. So if the omega-3 works, the difference in scores should be positive. The results are summarized in the table and box plot. So you have all of this table and the box plots. I hope you realize now that this is a matched pair situation, also known as paired data, also known as mean of differences, where we look at the difference of placebo minus omega. We really don't care much about these. This is what we want. This box plot is what we want. Next page. The researcher claims the omega-3 supplement will decrease the mean irritability score of all patients with medical conditions similar to volunteers. Is there convincing statistical evidence to support the researcher claim at a significance level of alpha equals 0.05? Complete the appropriate inference procedure to support your answer. So this is a typical, straightforward, no tricks hypothesis testing question involving matched pairs or mean of differences, where we're given that the difference is D equals placebo minus omega-3. And we're testing that this mean is positive. Since we're testing that the mean difference is positive, the H0 is that mu sub D is equal to 0, and the HA is that mu sub D is greater than 0. Now we need to check conditions. This hypothesis test of the mean of differences is actually a one mean test in disguise. So it adopts all the conditions of the one means test. The conditions are number 1, randomness, and number 2, normality. For something like this randomized experiment, where there was no sampling, no random selection, there's no 10% to check. So we don't check the 10% condition for this. There is randomness because there is random assignment between pairs. That's how randomness is done for matched pairs. This condition is met. And number 2 is normality. N is 19, and that is less than our usual cutoff of 30. So we have to look for normality somewhere else. And the place where you can look for it is in this box plot. It is kind of symmetric, kind of not, but close enough. This condition is met, and we can say that all conditions are met. So now we do the test. On the AP, when you run a hypothesis test, they need you to identify the test by name or by formula. Well, then you flip over to the formula page to see if you can copy a formula. And you don't see anything involving the t-test. You give up on that idea, and now you have to identify the hypothesis test by name. The name of this test is a matched pairs t-test. And one thing I advise people to do if you have time is to put in the input. For a hypothesis test, the AP always requires both the test statistic and the p-value. This p-value is less than 0.05, so we reject H0. That's the end of the calculation. Now the last step is to write the conclusion in context. When you reject H0, then there is sufficient evidence that HA is true. I usually write there is sufficient evidence, but in this question, they use specific language. So I might as well use their specific language. And then the language that follows this spot should be an English translation of the alternative hypothesis HA. Fortunately, that English translation is in the question, so I might as well copy that as well. Of all patients with the medical condition. This word all here is actually important. It indicates that the conclusion is about the population, not just about the sample. Number 5. Wildlife biologists are interested in the health of Tule elk, a species of deer found in California. An important measurement of the Tule elk health is their weight. The weight of a Tule elk is difficult to measure in the wild. However, chest circumference, which is believed to be related to the weight of the Tule elk, can easily be measured from a safe distance using a harmless laser. A study was done to investigate whether chest circumference in centimeters could be used to accurately estimate the weight in kilogram of male Tule elk. For the study, wildlife biologists captured 30 male Tule elk, measured their chest circumference and weight, and then released the elk. The data for the 30 male Tule elk are shown in the scatter plot. We have a scatter plot with the x-axis is the chest circumference in centimeters, and the y-axis the weight in kilograms. Part A, describe the relationship between chest circumference and weight of male Tule elk in context. In context, don't say X and Y, say chest circumference and weight. There's a standard way for the AP to grade how you describe the relationship of a scatter plot. Do you want the strength, like strong or weak? You want the form, linear or nonlinear? You want the direction, whether or not it's a positive relationship going up together, or it's a negative relationship where one goes up and the other goes down. And the fourth thing is whether there are any special points, such as outliers or influential points. This looked linear, positive, and it's not quite strong. And the last thing I would look for is any influential points or outliers, and I don't see anything. Therefore, I'd say it like this. There is a somewhat strong, that's the strength, positive, that's the direction, linear, that's the shape, between chest circumference and weight of Tule elk, I guess male Tule elk, with no apparent influential points or outliers. 4 things they're looking for, 4 things I'm giving them. Following is the equation of the least squares regression line relating chest circumference and weight for the male Tule elk. Predicted weight is equal to that. And part B asks, the weight of one male Tule elk with a chest circumference of 145.9 is 204.3. Using the equation of the least square regression line, calculate the predicted weight for this male Tule elk. Show your work. Predicted weight of this male Tule elk. Sometimes I just copy down the question. Calculate the residual for this male Tule elk. Show your work. Well, this male Tule elk is 204.3 kilograms, whereas we're predicted to be 196. So for this same X value of 145.9, this number here is 196.17, whereas the actual value here is 204.3. And the residual is that length. The residual will be, you take these 2 numbers and just subtract them. Well, some of you may have trouble remember which one subtracts which one. Is it 204 minus 196 and end up with a positive number? Or is it 196 minus 204 and end up with a negative number? Well, the way I remember it is I treat the least square regression line like an x-axis. If I flatten it out, then it's kind of intuitive that this should be a positive and that should be a negative number. Therefore, I should take the observed number and minus the number on the line, minus the expected number. So the residual, observed minus predicted. So go to 204.3 minus 196.17 equals 8.13 kilograms. Part C, interpret the slope of the least square regression line in context. So here's the slope, and the slope in algebra means that for every actual 1 in X, that's how Y value is moved. So X here is the chest circumference. Y here is a predicted weight. So every actual 1, in this case centimeters, in chest, we expect the elk or the Tule elk to have 3.7 something extra kilograms in weight. Notice that I said expected. This is a predicted weight, not an actual weight. So that's the degree of uncertainty that comes with linear regression. We need to put that in the answer. Let's write it. For every extra or additional, in male Tule chest circumference, we expect an additional 3.4755 kilograms in predicted weight. Part D, the sambar, another species of deer, is similar in size to the Tule elk. The slope of the population regression line relating chest circumference and weight for all male sambars is 4.5 kilograms per centimeter. A wildlife biologist wants to determine whether the slope of the population regression line for male Tule elk is different from that of male sambars. Let beta represent the slope of the population regression line for male Tule elk. The wildlife biologist conducted a test of the following hypothesis using the sample of 30 Tule elk. H0 is that beta is equal to 4.5, that's the slope for the sambar. And HA is that beta is not equals to 4.5. The test statistic was calculated to be 3.408. Assume all conditions for inference were met. Determine the p-value of the test. The test for the slope uses the t-statistic. If you don't remember, go look in your calculator. See where it falls under. So under Casio, it under t and then reg. So you know that it uses a t-distribution. For the TI, the name of the test is lin-reg t-test. So again, you know it uses the t-distribution. So test of slope uses t-distribution. Have a t-distribution that looks like the normal distribution. It has a test statistic of 3.408. And because this is a two-sided test, two-tailed test, then that means there is a negative 3.408 back here. And then these two together makes the p-value. If this were a normal distribution, you know how to calculate this. For the t-distribution, you use a similar process on your calculator to find this number. So p-value is equal to the probability that t is less than negative 3.408 or t greater than 3.408. You can take one of them and multiply by 2. Well, then when you plug it in on your calculator, you realize you need the degrees of freedom. And you remember that, oh, my teacher taught me that, yes, the t-distribution comes with degrees of freedom, but I don't remember how it went. I know that for the mean test, degrees of freedom is n-1. Well, is this one also n-1? Well, it turns out it's not n-1, it's n-2. But if you don't remember that, I would do this trick. I would fake, let's say 5 points, x, y. And then I would run my test. So on the TI would be lin-reg t-test. On the Casio, it would be test t-reg, and see what the degrees of freedom is equal to. Well, you will find out that it will show DF equals 3. Then you say, aha, it's not n-1, it's n-2. So that's how you remind yourself that it's the degrees of freedom is n-2. So I write down degrees of freedom is equal to n-2 equals 28. And then I run the probability. And it's equal to 2 times this, which is 0.002. I'm going to write the word T distribution down here and also the word T here, because AP looks for defining the distribution by name or by formula. And sometimes they give you some more options. For example, sometimes they accept calculator speak. I'm just going to put T everywhere just in case. So p-value is 0.002, and then I now can write the conclusion. Sure enough, part II asks for a conclusion. Reject is not. There is convincing statistical evidence. And then I write down all of that. That's the parameter in the context. Is not 4.5. And the unit of the slope is kilogram per centimeter, but they have not been using it, so I'm not going to put it in. For this question 6, I benefited a lot from discussions with other AP readers, especially with Jay Windley at Cal Poly Pomona. So I'd like to thank Jay Windley for that. His contributions helped a lot with part B and part D of this solution. I hope I understand his ideas correctly. So if there are any errors, those are mine, not Jay's. Question 6. Question 6 on the AP Stats exam is always what's called an investigative task, where you're led through the steps that allows you to discover some kind of statistics that is outside the typical AP Stats curriculum. A jewelry company uses a machine to apply a coating of gold on a certain style of necklace. The amount of gold applied to a necklace is approximately normally distributed. When the machine is working properly, the amount of gold applied to a necklace has a mean of 300 milligrams and standard deviation of 5 milligrams. The necklace is randomly selected from the necklaces produced by the machine. Assuming that the machine is working properly, calculate the probability that the amount of gold applied to the necklace is between 296 and 304. Assuming the machine is working properly, if it's working properly, then first of all, you'll be normally distributed. Actually, approximately normally distributed comes before when the machine is working properly. So it's going to be approximately normal all the time. When it's working properly, the mean is 300 and the standard deviation is 5. Question A is a normal distribution question. Well, for any probability distribution question, they want you to show the distribution by name or formula, the parameters that define that distribution, and the interval over which you're calculating your probability. People usually don't identify the normal distribution by formula. That happens a lot more often with the binomial distribution. People would just usually define by name by writing the word normal or using the math notation capital N. The parameters that define the normal distribution would be mu and sigma, or sigma square if you're used to doing that. And then the interval of the probability would be things like x is greater than a certain number, or x is between some two numbers. And then a lot of times they would accept a well annotated graph as showing all of this information. Let me show you how to do that with a graph. You draw something that looks kind of bell-shaped. A lot of rubrics in the past have accepted it as drawing a normal distribution. So by doing this, I've shown the interval where the probability is calculated on. I need the mean and the standard deviation. And while here, even though I said a bell-shaped curve would be acceptable, just to be on the safe side, I'm going to write the word normal. Alternatively, I can say that the gold amount is distributed according to the normal distribution. And then I have my interval by writing P open parentheses and then the two numbers. And the answer is 0.576. Next page. The jewelry company wants to make sure the machine is working properly. Each day, Cleo, a statistician at the jewelry company, will take a random sample of necklaces. Each selected necklace will be melted down and the amount of the gold applied to that necklace will be determined. Because a necklace must be destroyed to determine the amount of gold that was applied, Cleo will use random samples of size n equal 2 necklaces. That sounds a little bit different from class already, right? In class, we never do things with samples of 2. It's always like a very large number. Cleo starts by considering the mean amount of gold being applied to the necklaces. After Cleo takes a random sample of n equals 2 necklaces, she computes the sample amount of gold applied to the 2 necklaces. Part B, suppose the machine is working properly with the population mean amount of gold being applied of 300 and standard deviation of 5. So part I, calculate the probability that the mean amount of gold applied to the sample, to a random sample of n equals 2 necklaces will be greater than 303 milligrams. All right. Even though we have a very small sample size, n equals 2, in this case, central limit theorem still applies because the population distribution of the gold is given as approximately normal. By the central limit theorem, we can use normal distribution to calculate this probability. And again, normal calculation requires all of these identifiers. So let's make sure we do that. But before we do that, we have to justify using the central limit theorem and applying normal. So let's do that first. The sampling distribution of means is approximately normal because the original distribution is given as approximately normal. By the central limit theorem. And now we can determine the sampling mean and the sampling standard deviation. Sigma over square root of n. And now I'm doing all the identifying necessary for normal. I'm pretty sure I don't really have to do that because I already have the word normal here. I already have the mean here, and I already have this standard deviation here. But might as well. Greater than 303. And I get 0.1980. Support II. Suppose Cleo took a random sample of n equals 2 necklaces that resulted in a sample mean amount of gold applied of 303. Would that result indicate that the population mean amount of gold being applied by the machine is different from 300? Justify your answer without performing an inference procedure. Well, as a test taker, what do I do when they tell me not to do something? Well, I do it on the side. If I'm testing that the population mean amount of gold being applied by the machine is different from 300, then that means my H0 is that mu equals 300, and HA is that mu is not 300. The sample mean is 303. The z-score of this would be the test statistic. And this probability that I already calculated up here would be the p-value on the right side of it. This is the probability of getting a sample as extreme as ours. And extreme as ours is 303 or more. So that's the p-value. Now, however, the HA is that mu is not equal to 300. It's a two-tail test. So in order to do that, I need another tail on the left. And the total of the two of them will be my p-value. Well, one side is 0.198, so two sides must be 2 times 0.198. And then I can answer the question that way. But I'm not allowed to conduct an inference procedure, so I will quietly erase this. And I do everything that I would have done, but I would do it in words. I will pretend I didn't do it. So instead of using the word p-value, I will use a phrasing that means the same as a p-value. Specifically, the probability of getting a sample as extreme as ours. Per part BI, probability of getting a sample as extreme as ours on the higher side is 0.198. Therefore, the probability of getting a sample as extreme as ours either side is 2 times that, 0.396. Therefore, it is not an unusual event, assuming, remember I have to get this into a definition of p-value, assuming H0 is true. Basically, I'm saying that p-value is too high. And H0 is not rejected. You don't reject H0. Now I make the conclusion in context the same way I would have done inference, except I don't write out the actual inference because it tells me not to. Continue to the next page. Now Cleo will consider the variation in the amount of gold the machine applies to the necklaces. Because of the small sample size, n equals 2, Cleo will use a sample range of the data for the 2 randomly selected necklaces rather than sample standard deviation. Here's the investigative part. The part where you do inference on the range, which is something we've never done before in class. Cleo will investigate the behavior of the range for samples of size n equals 2. She will simulate the sampling distribution of the range of the amount of gold applied to the 2 randomly sampled necklaces. Cleo generates 100,000 random samples of size n equal 2 independent values from a normal distribution with mu equals 300, sigma equals 5. The range is calculated for the 2 observations. The simulated sampling distribution of the range is shown in graph 1. This process is repeated using sigma equals 8 as shown in graph 2, and again using sigma equals 12 as shown in graph 3. So here's graph 1 with sigma equals 5, graph 2 with sigma equals 8, it seemed to be spread out a little bit more to the right. And graph 3 with sigma equals 12 is spread out even more to the right. Part C, use the information in the graphs to complete the following. So part I, describe the sampling distribution of the sample range for random sample size equal 2 from a normal distribution with standard deviation sigma equals 5 as shown in graph 1. That's a very fancy way of just asking for this. Describe the distribution. How do we describe the distribution? Shape, which consists of two things. How many modes? Unimodal, bimodal, etc. And skewness. Center, spread, and any outliers. Unimodal, one mode, skew to the right, center, down here somewhere, and the spread. Well, normally you could describe a spread as standard deviation, but in this case, it's kind of hard to see what the standard deviation could be. So let's define the spread by where most of the points are. Most of the points are between those numbers. By the way, it's not the complete range because in theory, there are probably like some dots all the way going all the way out to infinity. Because if you think about picking 2 points from a normal distribution and calculating the range, it's totally possible that the 2 points are at like a billion positive and 0. So don't talk about the range because it's, I don't know if they'll mark you wrong for it, but it's actually not accurate. So I'm going to say that the vast majority of points are between 0 and 20. First, I'm going to copy down verbatim. Here's to be unimodal, with center around 5 to 9. There are outliers at sample range greater than 20. Part II, describe how the sampling distribution of the sample range for sample size n equals 2 changes as the value of the population standard deviation sigma increases. If you compare again at the beginning, it's like sigma equals 5. At sigma equals 8, it spreads out more. And at sigma equals 12, it spreads out even more. So that's what I will say, but I will also need to repeat everything else as well. The shape, the center, the spread, the outliers. Being unimodal and skewed right don't change, so I need to say that. But as the spread increases, the center also moves along with it. And then where the outliers are also moves further to the right. When sigma equals 8, the center is down here somewhere, maybe 10 to 15. And when sigma equals 12, center maybe so 15 to 20. And the spread also increases. At sigma equals 8, it goes almost all points are between 0 and 30. And at sigma equals 12, almost all points are between 0 and 40. outliers are at higher values as well. Next page. Cleo takes a random sample of 2 necklaces and calculates the sample mean amount of gold applied as 303 and the sample range as 10. Part D. Recall that the machine is working properly if the amount of gold applied to a necklace has a mean of 300, standard deviation of 5. Subpart I. Consider Cleo's range of 10 from the sample size n equals 2. If the machine is working properly with a standard deviation of 5, is the sample range of 10 mg unusual? Justify your answer. If the machine is working properly, then sigma equals to 5. So let's go look at the sigma equals 5 graph. Here's 10. It's unusual if it's rare for us to find a sample that extreme. Therefore, we need to look at this area. It doesn't look like 0.05, right? 0.05 is 1/20. That doesn't look like 1/20th of the graph. In fact, if I try to draw that area, it looks like about 1/5 of the graph, or maybe 1/6 of the graph. I'm going to pick a number. I'm going to say 0.15. On graph 1, probability that the sample range appears to be about 15%. And again, we're using the language of p-value without actually calling it a p-value. It is not unusual. Part II. Do Cleo's sample mean of 303 and range of 10 indicate that the machine is not working properly? So the question is, if it's working properly, would it end up with a sample mean of 303 and a range of 10? So we need an end in there. If the machine is working properly, then the probability of a sample mean as extreme as 303, actually as extreme as Cleo's, in either side is something we already calculated in part B, 0.396. And the probability of sample range is about 15–20%. And that's from part D. Well, DI right here. So the probability of getting both of these is the product of these two. And when you multiply, you get 0.0594, which is kind of high because we usually go by 0.05. And you're probably going to say, well, how can we multiply? How do we know that mean and range are independent? Well, mean and range are independent because once you have a mean somewhere, just like move the range accordingly. They don't change each other's probability. But how would you as a student know this? And for this, I benefited a lot from discussion with some of my fellow readers, specifically Jay Windley from Cal Poly Pomona, And so I'd like to thank Jay Winley for that. If you don't know the theory, you can tell by this problem, because this problem tells you that Cleo analyzes range based only on sigma. But analyzes the mean based on mu. And therefore, we justified in using the multiplication. And therefore, there's not sufficient evidence the machine is not working correctly. I hope all of this has been helpful. Check the description section if you want the videos to all the questions separately. The links are in there. Any comments, questions, feedback? If you think I was wrong in something, I especially love that you tell me about it in the comments section below. Like, share, and subscribe for more contents. And thanks for watching. Bye.